as we start IPv6, I always hear the same thing. It's all so complicated. It's too much to wrap my head around. This is due to the enlarged size of the address. Now, in our IPv4 address, we had 32 bits of data. It was very nice. Everything was nice. But as you can see, we're running into several chunks of 32 bits of data. We have 32 here, 32 here. That's 64 total. And we have 64 over here for a total of 128 bits. Moreover, this is in a hexadecimal format, not something we're used to using these days. We're used to that 32-bit format that we've seen our whole careers, right? So we really have to break this down to understand it. It's really not as scary as it lets itself on to be. So let's dive in for a moment. First off, the first 48 bits of any IPv6 address is called the global routing prefix, all right? So that draws a line right here. This is a part that's never going to change. We don't have to worry about it, all right? That's not our business. So that first part is already set aside. Next up, we have the subnet, or the next 16 bits. That's right. Subnetting takes place here at the /64 mark for our IPv6 addresses. Not at all like our IPv4 addresses where we subnetted all over the place, didn't we? Here, it's just in this middle portion where we have the subnet ID. That /64 is right here. This is /64. We subnet in the 16 bits right before it. So those 16 bits in there, that's where we really start to make our mark subnetting wise. Last but not least is the last 64 bits. The last 64 bits is actually the interface ID, and this is going to be our unique identifier on our networks. Think about that for a moment. I'm going to draw a line for you. This is the entire size of the IPv4 address scheme. Now remember, as I go up, that doesn't mean that this is twice the size. No. Remember, just one bit over here means I've doubled IPv4. Another bit, I've doubled it again. So just to this chunk right here, I've increased the size of the entire IPv4 address space, which is around 4 billion, right? I've doubled that number 16 different times just to get to this point. Doubled it. So that's 8 billion, 16 billion, 32 billion, so on and so forth. I keep going. 64 billion, 128 billion, 256 billion, 512 billion, 1 trillion, 24 billion. So I've gone way up. I've increased the scale by a lot, and we're not even here yet. That's how large the address space is for IPv6. Now, I know what some of you guys are saying, IPv6, that'll be long after I retire. Well, if you are in North America, Aaron has already handed out its last IPv4 address. Now, that doesn't mean we're completely out yet. They hand them out to ISPs, and then ISPs hand them out. So there's still another layer that needs to be depleted before we are absolutely completely out of IP4 addresses. But it's coming, right? We consume them at a faster rate every year. So IPv6 is not only on the horizon, I would really say that it is broken past the horizon, and now we are looking it dead in the face. In the next 5-6 years, I guess we would be moving to IPv6 at that point. So it's best to learn about this now. So once again, global prefix here, first 48. 48 to 64, that's where our subnetting takes place. Anything beyond that, that's our network, our unique identifier within our network, our interface ID. So let's look at the different types of address we have here. Now, first of all, I'm going to ask you a question here. Do you see anything missing? If I was in IPv4, I would expect to see 4 of these. I don't see 4 of these, I only see 3. What's missing in this picture? I'll give you a hint. Starts with a B. Ends with a T. R, S, O, A, C. Our broadcast, right? Our broadcast is missing. We don't have any broadcast traffic anymore. Instead, we have unicast, multicast, and anycast. That's it for IPv6. We are not going to broadcast at the layer 3 level. Now, this unicast is direct one-to-one communication. Nothing important, nothing different there. That's when we know who we're talking to. We're going directly to that specific node on the network. Multicast is for anyone who has joined a group. So if we have a group, and these addresses usually start with F00, that's usually their global identifier. FF00 double colon, if that's what you're using, that's the multicast address. We're trying to reach something where multiple nodes have joined that group. Multiple nodes are listening to this multicast address, whatever it is. Usually that's last name. Last but not least, we have the Anycast address. Now, the Anycast is a very interesting thing. It did exist in IPv4, and what it does is it delivers to the nearest node with that IP address. That's right. We're going to have multiple nodes with the same IP address. We used to have what's called Anycast rings. They're used a lot to diffuse a distributed denial of service attack. For those of you who work at that level, if you're high enough in there, you know what I'm talking about. So what I have is a bunch of nodes in a circle. So on the DMZ of my large network, right? I got a network here. This may even be placed in different ISPs if I want. Okay, so on the DMZ of my enterprise network inside of an ISP themselves. And what happens is routers actually route to the closest available service. So all of these would have, I don't know, 2000 DB8, whatever, double colon 2, right? So all of this has the exact same service enabled. So these servers are all mirrored, providing the same service, and they're all carrying the same IPv6 address. Well, routers will simply route to the nearest one to them. So the router up here, the nearest service node to them is here. So it's going to hit that server. And what happens is with this Anycast ring, if anything happens to this node right here, what happens is it drops out. The router advertisement fails, and we have another way to get there, right? There's another one that exists. The router finds a better way through dynamic routing protocols, whether it's BGP or some other way to advertise that particular route into the environment. So Anycast has been used for a long time. It is delivery to the shortest path, whatever shorter, closer to our particular where we're leaving from in our environment.